Electric aviation is bound by a strict physical limit, the relentless pull of gravity against the heavy mass of energy storage. The more power a drone needs to stay aloft, the heavier its energy source must be, quickly yielding diminishing returns. For standard commercial UAVs, this dynamic creates an absolute performance ceiling. Drones relying on lithium polymer, or LiPo, batteries, the standard rechargeable chemistry used in most electronics, hit a hard endurance wall at roughly 20 to 40 minutes of flight time. This line graph maps endurance time across power sources. LiPo batteries tap out quickly. Gasoline engines push the range to 3 hours. But hydrogen fuel cells break the scale. With energy density 5 times higher, hydrogen systems push missions past the 10-hour mark. Achieving true multi-hour electric flight means engineers cannot simply build a better battery. They must abandon traditional battery-based designs and adopt a completely different thermodynamic system. Unlike a battery-powered drone, which acts as a flying storage container for pre-charged electricity, a fuel cell drone operates as a miniature mid-air power plant. It generates its own electrical current in real time. This provides stealth and environmental advantages over combustion platforms. Generating electricity through chemistry results in an exceptionally low acoustic signature and zero carbon emissions. Logistically, it eliminates charging bottlenecks. Instead of waiting hours for a battery to recharge, operators can swap an empty hydrogen tank for a full one in minutes. Realizing these gains in endurance and payload requires a ground-up re-engineering of the drone's internal power architecture. Hydrogen represents a significant architectural change that alters the aerodynamic profiles and weight distribution rules of standard UAV design. This wireframe schematic shows a heavy-lift multi-rotor UAV base frame. Notice the internal void designed for gas storage. First, a high-pressure storage tank secures raw hydrogen at the center of mass. Next sits the fuel cell stack, linked directly via a high-pressure fuel line. The aerospace industry standard for this component is the PEMFC, or Proton Exchange Membrane Fuel Cell. It dominates UAV architecture because it provides high power density, relatively lightweight, and the ability to start up instantly. This cross-section illustrates a single PEM fuel cell. Hydrogen flows into one side, oxygen into the other. A catalyst splits the hydrogen, forcing protons through the central membrane. Stripped electrons detour through an external circuit, powering the motors, before recombining into pure water vapor. This continuous, silent chemical reaction means the drone does not carry the dead weight of a depleting battery. It simply generates a steady, reliable stream of electricity until the gas runs out. By extracting power from a lightweight gas rather than dense, heavy metals, engineers maximize the power-to-weight ratio, allowing flight durations that were previously impossible for electric platforms. But the PEM fuel cell has a specific operational limitation. While it provides an incredibly deep well of steady energy, it reacts poorly to sudden, massive spikes in power demand. For a UAV, this is a major obstacle. Drones require intense, immediate bursts of peak power to execute vertical takeoffs, fight sudden wind shear, and perform aggressive maneuvers. This block diagram maps the hybrid architecture, pairing the fuel cell with a small lithium battery. During cruising, the fuel cell handles the steady electrical baseload, but during takeoff or maneuvering, the lithium battery instantly injects a high amperage burst to keep the drone stable. The crucial element here is the onboard power management electronics. This computer must intelligently and seamlessly switch between the two power sources hundreds of times a minute to prevent stalling in midair.
This hybrid system adds a layer of efficiency. During low-power cruising, the fuel cell trickle charges the lithium buffer battery, ensuring the drone always has enough peak power in reserve for an emergency maneuver. Successful multi-hour drone flights are never purely hydrogen-powered. They rely on a delicate hybrid integration, marrying the deep endurance of a fuel cell with the explosive agility of lithium. Keeping this hybrid system airborne exacts a heavy engineering toll. In aviation, physics always demands a trade-off. This exploded view illustrates the mandatory support penalty. A fuel cell requires thermal cooling systems, complex control boards, and heavy high-pressure tanks. Then there is the financial bottleneck. The internal reactions of fuel cell stacks rely heavily on rare, expensive platinum catalysts. This complexity creates a scale problem. The baseline weight of these mandatory support systems makes hydrogen technology extremely poorly suited for small, everyday consumer-sized drones. The hardware simply weighs too much. Furthermore, operators face a severe logistical hurdle. While swapping a tank is fast, the global supply chain for sourcing pure, highly pressurized hydrogen is currently very limited. Finally, managing highly flammable gas stored at extreme pressures requires stringent safety engineering, especially inside an unmanned vehicle that operates in volatile airspace. Due to the massive systemic weight and cost, hydrogen power is relegated to heavy lift, enterprise or military UAVs, where the demand for ultra-long endurance justifies the extreme complexity of the build. Despite these hurdles, there are specific operational domains where heavy-lift hydrogen drones outperform all other platforms. They dominate beyond visual line of sight, or BVLOS, operations. This includes mapping massive solar farms or conducting hundreds of miles of continuous pipeline inspection in a single flight. In military and defense logistics, specialized hydrogen platforms can carry up to 50 kilograms of payload over ranges spanning 300 kilometers. This split-screen graphic illustrates a significant tactical advantage over lithium batteries: superior performance in freezing temperatures. Standard LiPo batteries suffer catastrophic voltage sag and capacity loss in sub-zero weather, but the internal thermodynamic reactions of a fuel cell keep it operating at peak efficiency regardless of the ambient cold. This cold weather resilience makes hydrogen an effective tool for high-altitude reconnaissance and winter disaster response missions. In extreme environments and sprawling long-range missions, hydrogen moves from a niche alternative to the primary viable method for maintaining electric propulsion. At the leading edge of aerospace research, engineers are pushing flight times past the 10-hour mark. The next major leap in energy density involves abandoning pressurized gas tanks in favor of cryogenic liquid hydrogen storage. Pioneer companies utilizing liquid hydrogen prototypes have surpassed existing endurance records. Experimental platforms developed by firms like Hylium have exceeded 13 hours of continuous flight. A parallel evolution is happening on the ground with the development of autonomous hydrogen refueling stations. These act as robotic drone airports, capable of swapping tanks without human intervention. Pairing AI-driven fleets with these automated refueling hubs will create continuous, hands-off surveillance and logistics networks capable of operating 24 hours a day. Driven by stricter environmental regulations and rising demands for remote delivery, market analysts project hydrogen technology will likely lead the long-range UAV sector. By bypassing the physical limits of lithium chemistry and adopting a radically different power architecture, engineers have expanded the operational envelope of electric flight, enabling the multi-hour persistence required for modern industrial and defense logistics.